The next problem I want to look at is problem number 6. And here again, I do have an option. It's up to you. I could use the ratio test. I could use the root test. Or I could simply say, you know what, it's easier than either of those. This problem is actually geometric. Geometric series are very easy to predict. All what you have to do is find r. So you could say, you know what, 2x is taking the place of r. As long as that's less than 1, this series converge. And like I said, the author would really like us to get this to be a positive 1. So if you divide by 1 both sides, this would be my radius of convergence. That part is done. And if I solve this, not much to do. X is between negative 1/2 and positive 1/2. That would be the interval of convergence. So this is part A. Part B, it's automatically absolutely convergent. And C, since x equal 1 it diverge and negative 1 diverge because of geometric series, this either you say none or nowhere. This is nowhere conditionally convergent. The next problem I'd like to look at is problem number 8. And here we're looking at a series, and again, this series is definitely not matching a geometric series. So we're going to take the limit as n approaches infinity of a sub n plus 1. Divided by or multiplied by the reciprocal instead of dividing by a fraction. Now, like we said in class, since you're taking the absolute value, you could pretty much ignore the negative 1 to the n that's going to be absorbed by the absolute value and just focus on the rest. So very similar to problem number 4 that we did. Limit as n approaches infinity, and x plus 2 is a constant. We're looking at n over n plus 1, and we know that's infinity over infinity. Again, either you divide by the highest power term or the denominator like we did back when we found the horizontal asymptote, or you simply apply L'Hopital only on the ends, and that would be 1 over 1. So I'm left with absolute value of x plus 2. Set that to be less than 1. Since this is a 1, automatically I got my r. And the interval of convergence, you just solve this inequality. Subtract 2 from both sides, and there it is. So up till now, part A, the radius of convergence is 1, and the interval of convergence is negative 3 to negative 1. And now, we would like to see, well, B automatically, it's absolutely convergent for negative 3 to negative 1. The only part left would be part C. And part C, you're checking for conditional convergence. You have to test if x equal negative 3, what would happen? Or if x equal negative 1, what would happen? So, if I substitute x equal negative 3 in for that x, that would be the series n equal 1 to infinity, negative 1 to the n. And if I put negative 3 plus 2, that's negative 1 to the n over n, that would become the series of negative 1 to the 2n, which is always positive, pretty much. So this is a p series, n equal p equal 1, therefore diverge, so I can't have negative 3. How about negative 1? If I let x equal negative 1, again, substitute that in for x, n equal 1 to infinity, negative 1 to the n. If I put a negative 1 plus 2, that's 1 to the n over n, and we recognize that this is positive, decreasing, and the limit as n approaches infinity of 1 over n equals 0, therefore converge by alternating series test, therefore conditionally convergent for x equal negative 1 only. We're going to be discussing this in class, so if you have any questions, just hold on to those. Next problem I'd like to look at would be problem number 10. So, again, I'm going to upload a copy of this PDF in Blackboard. You can view it. The same idea. I glance at this, say, okay, well, let's see how this is going to work. In this case, this is not geometric. I'm going to take the limit as n approaches infinity of x minus 1 to the n times x minus 1 to the 1 over the square root of n plus 1 multiplied by the reciprocal. We've kind of did this a bit more times than we like in the previous sections. Limit as n approaches infinity, and I'm going to cancel this out, x minus 1. And here, if I combine those and divide by the highest power term of the denominator, L'Hopital wouldn't be wise here. It's a bit messier than you like, so might as well divide by the highest power term of the denominator, and this limit will be the absolute value of x minus 1. So there, let it be less than 1. Again, since this is a 1, automatically that's my radius of convergence. And my interval of convergence is simply you solving this. So, the radius of convergence is 1, and the interval of convergence is 0 to 2. This is part A. And from this, I know part B automatically, absolutely convergent on this interval. That's always going to be the case. Since I use the ratio test, now I have to really test what happens at the endpoints. The endpoints being when x equal 1, or simply, if I solve this, what happened when x equals 0 and what happened when x equals 2? So at x equals 0, if I replace this x by this 0, I'll notice I'll be looking at the series n equal 1 to infinity of negative 1 to the n over radical n. So I know this is positive. Like we said, if n only appears in the denominator, just say decreasing, and that's okay. You don't have to show anything. And we know the limit as n approaches infinity of 1 over radical n equal to 0, therefore converge by alternating series test. So this is what we know for part C. Conditionally convergent, so far it's at x equals 0. And how about x equal 2? If I take x equal 2 and replace that x by it, that will be the series n equal 1 to infinity of 1 to the n over radical n, which is really the series n equal 1 to infinity of 1 over n to the 1/2. This is a p series, p equal 1/2 less than 1, therefore this diverge. So that's pretty much it. I can't have x equaling 2. And that's pretty much how we do all of those. I have one more I want to tackle out of those before I move to the end of the section and conclude. So if I look at problem number 12, let's see what 12 is. There it is. If I take problem number 12, there are a couple of exceptions. If I apply the same idea, again, this is not geometric because the n factorial is messing things up. So if I take the limit as n approaches infinity of the absolute value of 3 to the n plus 1, x to the n plus 1 over n plus 1 factorial, that's the limit as n approaches infinity of, oops, messed up, that's okay, like I said, this is my first attempt, divided by, so I'm going to multiply by the reciprocal, and and that's going to be 3 to the n times 3 to the 1 times x to the n times x to the 1 over n plus 1 times n factorial, like we did over and over in the previous section. And here, x to the n cancel out, n factorial cancel out, 3 to the n cancel out. I'm left with the limit as n of which is infinity of 3x over n plus 1. Keep in mind that x is independent of n. This limit equals 0. Using the ratio test, and I took a limit and I got it to be 0, which means that's going to be less than 1 for all x. No matter what x value you choose, that limit will always be 0, which means what? Therefore, the radius of convergence, we say anything, infinity really, and the interval of convergence is really negative infinity to infinity. For any value of x, this factorial is going to dominate. That's part A. Part B, absolutely convergent. Well, that's everywhere as well. And obviously, conditionally convergent nowhere. I'm going to write this a bit nicer. I'm getting more comfortable with this now, making mistakes. You have